Alrighty then. Welcome back, my humble slaves, to the destroying nature, the withering nature of physics and mathematics. Here you see in front of you the psychotic madness that is nuclear decay. Now, I suppose one could say this isn't strictly nuclear decay. It could be the decay of anything in which the decay rate depends on itself, but that is another subject for another time. For now, we're just going to stick to the mathematical, physical nature of the thing. What in the fuck are we looking at? The pink bits are the amount of stuff at any particular time, as we see the time moving down here in the red, and that depends on some quantity called our decay constant we have here in the green, and as mentioned, wherever the hell we are on this pink curve is the amount of stuff we have. So, what the hell does that all mean? Well, top left here, we have a representation of this equation. So, one can consider the blue here being n, obviously the red being t for time, and the lambda here, this little funny upside down y, it's a Greek letter, being the decay constant. Now, n's the amount of stuff. So, at any particular time, as we see here, time, the equation reads time multiplied by the decay constant, multiplied by negative here, all to the power of the natural number, which if you don't know what a natural number is, go look it up, or I might do another video, we'll see. Multiplied by this NO factor. What the hell is NO? No. No is an initial amount of stuff that I've started off with at the start of my experiment when I press that button on the timer and I start looking. It's the initial quantity that I start off with when I start my timer. So if I have a kilo of stuff at the start of my experiment, that initial 1 kilogram is NO. Here we have an initial quantity that I have set where A here takes the place of our NO, and that is 0.8. So one can imagine setting up some experiment, and there's some collection of atoms, and those are atoms of a particular type. So let's say uranium, doesn't really matter, and we have 0.8 amount of those atoms. Could be grams, could be kilograms, could be micrograms, doesn't really matter what, but we have some quantity of those atoms, whatever those atoms happen to be. Now, if we look across this plot, right, if we start here, right at the corner, right at that zero there, alright, there's an errant C sitting around, don't mind that C. So, at that very point where we begin, that line cuts through 0.8. Now, in fact, what we can do is, if we say increase the amount that we start with, let's increase it to say 1. If this will let me, there we go, 1. Okay, so we're just going to zoom out a bit, there we go. So as you can see, you just get a slice right through 1, right at time 0. And as time continues on, as time ticks along. If our decay constant is 0, where it is here, we just tick along. If this lambda is 0, then time times 0 at any time will be 0, and we just continue on with the amount. There is no decay, basically. So what is our decay constant? Now that poses that question, right? Because clearly this decay constant has some effect. We'll find, we have found, on the quantity that we have. So a decay constant is essentially all of the physics of the object wrapped up in a little value. So when I say it could be any atom, it could be uranium, it could be plutonium, it could be, hell, it could be anything, right? It could be to helium. There's a whole bunch of physics, a whole bunch of quantum physics, a whole bunch of nuclear physics that goes into describing how quickly or how slowly the stuff decays into other stuff, right? Just have a lump of uranium on the table. How quickly does that uranium decay into its byproducts? And there's a whole lot of physics behind that, right? But at the end of the day, the mathematics of any of those problems doesn't change, right? You're still going to have some n, right? You're still going to have, at some point in time, you know, certain amount will have of the stuff will have decayed, and it's depending on how much stuff is left, right? You know, you got some amount of plutonium, and at some point in time you'll have half the amount of plutonium, and at another point in time you'll have a quarter of that. We're just going to say, don't worry about it. Don't worry about it. Let's just plug it. Let's just find some number to multiply by time so that our mathematical formula will accurately represent the quantity that we have at any particular time. And that's our lambda here. So, now if we ignore, so I'm just going to ask you to ignore the negatives here. We can actually get rid of them, but so now that I've gotten rid of the negative axes, you can still see the plot projected into the negative axes, but in a way that's actually kind of helpful to describe it. It's not really relevant, at least right now. What is relevant right now is the fact that as we look at this decay constant, and as it increases, we see that, okay, let's look at on top. Right, so we're moving up here, so moving up in time, so we're increasing in time. We started off with a quantity of 1, and if we have a decay constant of 0, that means that nothing decays, and look at that, nothing decays, it just stays along at 1. That line stays along the 1 thing. Now, let's move over to a decay constant of 0.5. So, if you're paying attention to the description of the decay constant, you would assume now that as we increase the decay constant, the rate at which we lose stuff is going to increase. So we saw that with a decay constant of 0, n will equal no, or for all time. And that's not very interesting. But what is interesting is if we increase that decay constant to say 0.5, now if we follow along the 0.5 line, which starts here, so all of these start at 1, as you can see. So no matter what, when we start at 0, so no matter what, when we start at 0 seconds, we are always at 1. We always start off with a quantity of 1, which makes sense, right? Doesn't matter what the decay constant is, it's the same amount of stuff that I started with, no matter what my decay constant, which you see along this line. Now, as we move across this line, so we move to our 0.5, we come down, and so we start off at 1, then as the seconds tick away, 1 second, move down, down. We move down, and the quantity of stuff slowly decays, which is exactly what we expected. Now if we move to decay constant at 1, that decay is a little quicker and moves down to something that is close to 0 much quicker. In fact, we can zoom in here, which should give us a much more interesting viewpoint. So if we start at 1, we can pop over to, what's this, 1.6, and we'll start to move down a little quicker. And you know what, let's just turn off that. There we go, that's better. So as you can see, if we take a really sharp side view here, as we increase our decay constants, our nuclear decay increases with time. So we can look at this another way, right? We can just flip the damn thing, and this is the lovely nature, and this is why we have this f equals x line, because as you can see, this plot is symmetrical around this, right? So we can actually almost we can almost swap our time and decay constant variables here, and think of it this way, right? So for a particular time, right, our decay constant is going to decrease our quantity, or perhaps at any particular moment in time, a higher decay constant is going to result in a smaller amount of stuff left. So our n is going to be smaller. So in a sense, that whenever you're solving, or if you plan to solve this equation, or plan to play around with this, it can help to imagine the nuclear decay equation. It's a kind of symmetric equation, right? Because your time and your decay constant are interchangeable. It's really only your initial quantity that has some kind of, global effect, right? So as we mentioned, we can move this up, we can move this down, and the interesting thing too is that this is symmetrical around the negative axis. So if I pop over and reinstitute these, so if we take a neg, right? Because if we look at our equation up here, if I say time is negative and my decay constant is negative, well, that cancels negative. Negative times a negative is a positive, that cancels out, and so you essentially have the same equation going back. Not really useful in a physical sense, not immediately useful, but it is helpful to think that if you reverse the time, essentially, if I have this block of uranium that's, say, 1 kilo block of uranium, that, let's say that came from somewhere else, right? Let's reverse the time back. One can imagine, say, this quantity that I have right now, 0.7, actually, I'm starting the clock from when there's 0.7 of that 1 gram left. If I reverse the time back, I should start to get, there we go, I should start to see my line come back up to 1 at same kind of rate with the same decay constant, as long as it's the same stuff, right? But yeah, because this equation is reversible, you can use this equation at any point in your decay and start from there, and then move backwards and see where you came from, right? Because if I imagine, as I said, so if I would imagine that the origin here doesn't start at 0 seconds, it starts at, say, 1 second, and I'm starting here at 0.7. So another way to say this is, imagine I have a stopwatch and I'm pressing the go button on my stopwatch at the point in time in which there is 0.7 grams or stuff of uranium on the table. then what I can do is I can go backwards. And I can go, right, well, let's go backwards along this equation, and I can trace where if I have the right decay constant, I'm not quite sure what the decay constant of uranium is, but I can then walk backwards. I can go, okay, where was it 1? Okay, let's say for some random decay constant, it was here, and there we go. So now I can trace back. I can find out how much stuff I started off with. Not only that, I can figure out when I started off with that stuff. So not only can you use this equation for nuclear decay, you can go back the other way and figure out what amount you had in the first place. Beautiful, right? Gorgeous. We can also figure out, we can assume a negative decay constant. Alright, well, if we were to take a negative decay constant, then we actually then start to consider, well, what happens. Essentially, a negative decay constant would be an increase, right? Because if our decay constant was negative but time was positive, well, negative times the negative out the front of that exponential would be positive, and so what we'd end up getting is a increase in the amount of stuff per time. But our plot does not really show that very well because it gets pretty large pretty quickly. But you can kind of see it if we pop over here. We look, so that's a 0 line, our decay constant of 0. If we start going back past this point, so this is the positive direction, this is the negative direction, start going past that point, we start to see things increasing. So then we can talk about, say, nuclear, I suppose what's the opposite of decay? I don't know. Nuclear generation, I suppose. But really, all I want to do here is just come and get to the find some fundamental little fascinating bits about this equation using the three-dimensional plot. And hopefully you found out something new and interesting about the nuclear decay function. Thank you very much.